I'm going to work an example problem that involves tension force and gravitational force and equilibrium of forces. So in this problem, we're told that we have a 50-meter long horizontal cable or wire. Maybe it's an electrical cable, or maybe it's a telephone cable. And a 1 kilogram bird sits on the middle of the cable, stands on the middle of the cable, and the cable deflects or sags by 0.2 meters, 20 centimeters. And based on that information, the length of the cable, the sag of the cable, the bird's mass, we've got to figure out the tension in the cable. And to figure out the tension in the cable, this means analyzing the forces on the cable and understanding the equilibrium of the cable. Let me start by drawing a picture. So I'm going to draw the cable and the bird on the cable, and then I'm going to add the forces that are acting on the cable. So here's the cable and here's the bird standing on the cable. And the cable's length is 50 meters. And the cable sag is 0.2 meters. Obviously, I haven't drawn it to scale, but I am depicting the length of the cable and the sag of the cable. And the bird's mass, we're told, is 1 kilogram. There are 3 forces on the cable, and in particular, 3 forces at the center of the cable where the bird is standing that I want to sketch. Let me change color here. One force that is acting on the cable is the force of the bird on the cable, and that force is equal to the weight of the bird. And the weight of the bird is mg, mass times acceleration of gravity. If the bird's mass is 1 kilogram, acceleration of gravity is 9.8 meters per second squared. So the weight of the bird is 9.8 meters. I'll just write that down. So that's one force that's acting on the center of the cable. And then up and towards the left and up and towards the right are the 2 other forces. There's the tension on the left and the tension on the right. So those are the 3 forces. Now remember, these forces are vectors. So they have a size and they have a direction. The weight is a vector. It has a size and it has a downward direction to it. So that's a picture of the forces that are acting. There's one little bit of trigonometry I want to do before I actually go ahead and solve the problem. And so maybe I'll just work that out over here on the right. There's a triangle in this problem. So the triangle that's in this problem is made by horizontal and a vertical and half of the cable. It could be the left hand or the right hand half of the cable. So the horizontal is from the cable support on the left to where the bird is standing. That would be half the length of the cable, 25 meters. The vertical is the sag of the cable. That's 0.2 meters. And the hypotenuse, that is the cable itself. So there is this right angled triangle. There's actually one on the left and one on the right in this problem. And I want to figure this angle in here. I'm going to call this angle theta. It's the angle of the cable with respect to the vertical on the left or on the right. And we can calculate that angle using our trigonometric functions. And the one that we want is the inverse tangent or arctangent of the opposite side of the triangle. So that would be 25 meters divided by the adjacent side of the triangle. That would be 0.2 meters. So it's this length over the sag. And arctan of 25 over 0.2, which is arctan of 125, comes out to be, I worked it out here, 85.4 degrees. So it's nearly 90 degrees, but not quite 90 degrees. Anyway, that's a useful bit of trigonometry for us as we solve the problem. Now I'm going to go on to really solve the problem. The first thing I want to start with is this idea that the bird and the cable are in equilibrium. The bird's just sitting there, happily sitting there on the cable. And the bird's not moving around, the cable's not moving around. The bird and the cable are in equilibrium. The sum of the forces on the cable must add up to 0. And so that equilibrium condition, let me just write it down, that the sum of the forces add up to 0, in this case, is that the tension on the left plus the tension on the right, what I call T1 and T2, plus the weight, must add up to 0. Again, remembering that each of these forces is a vector with a size and a direction. Now, to figure out the tension, knowing the weight, we want to use this equilibrium condition. And to use this equilibrium condition, I'm going to break it out into horizontal and vertical pieces. So that's sort of the mechanics of applying equilibrium, of using equilibrium. So let's start with horizontal. What does horizontal tell us? Well, the horizontal tells us that the weight, well, that has no horizontal component to that force. The only horizontal components are the tension force on the left, which acts towards the left, the tension on the right here, which acts towards the right. And so the horizontal components of the tension force on the left and right must be equal in magnitude. So T1 sine theta, that picks out the horizontal component of the tension, must be equal to T2 sine theta. That picks out the horizontal component of the tension on the right. And those two angles are the same. We've discussed that. So the sine thetas cancel out. And so the horizontal analysis tells us that the two tensions, T1, T2, they have different directions, but they have the same magnitudes. They have the same sizes. Now, we could have said that originally from the symmetry of the problem. The bird sits in the middle of the cable. And so because of the symmetry of the problem, those two tensions must be the same. There's nothing to distinguish really the left-hand side from the right-hand side. But the math, the analysis also told us that the two tensions are the same. And from now on, I'm just going to call that tension, I'm just going to call it T. T1 equals T2 equals T. The magnitude of the two tensions, T1 and T2, are the same. We're going to call them T. Now let's look at the vertical. So in the vertical, there is two upward forces. There's the vertical component of the tension T1 and the vertical component of the tension T2. And then there's one downward force. There's the weight of the bird on the cable. And so the two upwards forces, the two tensions, must be balancing the downward force from the weight of the bird. So 2 times the tension times cosine theta, that picks out the vertical components of the tension forces, must be equal in size to the weight of the bird. And so that's what the vertical analysis is telling us. And if you look at this equation, so we're interested in the tension in the cable. Well, we can turn this equation around for the tension in the cable in terms of the weight of the bird and the angle of the cable, which was a reflection of the sag of the cable. And so the tension T is just the weight of the bird divided by 2 times cosine of 85 degrees. And if we calculate this, 9.8 newtons divided by 2 divided by cosine 85.4 degrees. I calculated it earlier on, and I got 61.3 newtons. And so 61.3 newtons is the size of the tension force T1 on the left. It's the size of the tension force T2 on the right. And so we've analyzed that using our understanding of the forces that are acting and a diagram, a sketch of the forces that are acting. That was gravity and tension, and using our understanding of the equilibrium, that the sum of the forces was 0 because the bird and the cable were stationary and staying stationary. So it's a nice example. This problem is a nice example of analyzing forces, sketching forces, breaking those forces down into horizontal and vertical components, applying equilibrium of forces to understand the sizes of the various forces.